No alkyl halides are colorless. For example, methyl bromide or bromomethane is a colorless gas that can be used as a pesticide. However, this use is being phased out due to its toxicity. Historically, it was used as an industrial fire extinguishing agent. Methyl bromide is also known to be an ozone-depleting chemical. The alkyl bromides and alkyl iodides may develop a color when exposed to light. For example, ethyl bromide turns yellow when exposed to light and air. Many volatile alkyl halides have a sweet smell, but this may not be noticeable unless the concentration is relatively high. Lower alkyl halides, including methyl chloride, methyl bromide and ethyl chloride, as well as some chlorofluoromethanes, are gases at room temperature. Higher alkyl halides are liquids or solids. You have already studied that the carbon-halogen bond in halogen compounds is polar. Due to the greater polarity and higher molecular mass of haloalkanes as compared to the parent hydrocarbons, the dipole-dipole and van der Waals forces of attraction are stronger in these compounds. Hence, haloalkanes have considerably higher boiling points than those of hydrocarbons of comparable molecular mass. For a given alkyl group, the boiling point increases with increasing atomic weight of the halogen. This is due to an increase in the magnitude of van der Waals forces of attraction with an increase in size and mass of the halogen atom. Thus, among the alkyl halides, alkyl iodides have the highest and alkyl fluorides have the lowest boiling points. For a given halogen, the boiling point increases with an increase in the number of carbon atoms in the chain. This is again due to the increase in the magnitude of van der Waals forces of attraction with an increase in the size of the carbon chain. The boiling points of isomeric haloalkanes decrease with an increase in branching. This is due to the fact that with an increase in branching, the molecule attains spherical shape with less surface area. This results in a decrease in the magnitude of van der Waals forces and hence the decrease in boiling point. Thus, among the isomeric butyl chlorides, the straight chain isomer, N-butyl chloride, has the highest, while tertiary butyl chloride has the lowest boiling point. The haloalkanes are only very slightly soluble in water. Why? For a haloalkane to dissolve in water, energy is required to break the attraction between the haloalkane molecules and the hydrogen bonds between the water molecules. As new attractions between the haloalkane and water aren't nearly as strong as the original hydrogen bonds in water, less energy is released during this process. Thus, haloalkanes are sparingly soluble in water. Haloalkanes do tend to dissolve in organic solvents. The intermolecular attractions that form between haloalkanes and the solvent molecules have similar strengths as the attractions being broken in the separate haloalkane and solvent molecules. Alkyl fluorides and alkyl chlorides are less dense than water. In a mixture with water, alkyl fluorides and alkyl chlorides would be the upper layer. Alkyl bromides and alkyl iodides are denser than water. In mixtures with water, alkyl bromides and alkyl iodides would separate into the lower layer. Increasing the number of halogen atoms increases the density of the compounds. Aryl halides are polar molecules due to the presence of the polar carbon-halogen bond, but they are less polar than alkyl halides. Aryl halides have physical properties very similar to alkyl halides. We should make special note of the isomers of dihalobenzenes. If we compare the ortho, para, and meta isomers of dichlorobenzene, we see that their boiling points are nearly the same. However, the para isomers have higher melting points. The greater symmetry of the para isomers fits better into the crystal lattice, making the para isomers melt at relatively high temperatures. Aryl halides are practically insoluble in water and are denser than water. Here is a problem for you. Arrange these compounds in increasing order of their boiling points. Let's start by drawing the structure for each compound. All the three structures contain one chlorine atom. Since the boiling point increases with an increase in the number of carbon atoms, we would expect 1-chlorobutane with its 4 carbon atoms to have the highest boiling point. The other 2 compounds have 3 carbon atoms each, but 1-chloropropane is a straight chain, while isopropyl chloride is branched. Branched molecules have lower boiling points. So, isopropyl chloride should have the lowest boiling point. 1-chloropropane is in the middle.